Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, thanks for attending. So I'm going to be talking about the early view. I'm at PSC. We do high-performance computing, very traditionally computationally intensive. I'm going to be talking about the expanding role of data in scientific analysis. So there's actually, think of it as a companion talk to the last talk of the day that Ralph Roski, who's in the front row, Mike Levine are giving. The titles on the agenda are very similar, but we were conscious to cover different things. So do both, please. Okay, so what I want to talk about, first of all, a few acknowledgments. They're in the slides. First of all, in terms of the abundance of data. So certainly, as was pointed out yesterday, it's kind of amusing how many of these talks have the same theme to part of them. We certainly had a nice collaboration through centuries between observation, theory, and pretty much single guys getting nice ideas. Along came simulation, large computing. Certainly let people do things a lot more aggressively, let them explore larger models, somewhat larger collaborations. What we have now, though, is certainly a regime where we have large-scale data collections. We don't have a pointer, do we? Okay. Thank you. Yeah. So we have large-scale data collections. And what these are really enabling is, as we've seen throughout this meeting, much larger collaborations. That's partly driven by just the nature of the additional work needed to do the theory, to implement the computer codes, to do the visual analysis, and to do other things. But it's also reaching out. In the Terra Grid, we call these things science gateways. And the idea is that by enabling user-friendly interfaces to some things, we can bring more people in and perhaps make them more accessible to others than the domain experts. And tied to all that, where this talk I want to address is also the coupling of that to the increased importance of doing large-scale data analysis and how that relates to overall I/O bandwidth, whether it happens to be on your local disk system or over the network. And hopefully that will all put together. Let's keep on generating some new good ideas.
With a nice green light bulb as opposed to...
Well, yes, the light bulb changes. Okay. The point of this talk, though, is not really the scientific applications. Mike and Ralph are going to talk about those much more detail at 4 o'clock today. I have some of those examples and motivators, but I really want to make the point that we've always known, at least some of us always recognized, the high-end simulation, you really need system balance. You don't just need lots of flops, you need balanced I/O performance, memory bandwidth, and so on. Well, we're looking at really large data, though, where large data today can be tens of terabytes. In the future, it will certainly be into petabytes and beyond. That certainly places bandwidth at a premium, whether it's I/O bandwidth or memory bandwidth, really both. The things driving that are simulation results, obviously. All the sensor data we've seen throughout this meeting and elsewhere, where sensor data includes experimental data that are coming in, the things like at UW in metagenomics and other fields. The socioeconomic things that may come from economics, from network analysis. Additionally, this data can be multimodal, it can be structured, it can be the nice CFD things that the NSAT example that was brought up before, those having nice gridded data. It can also be highly unstructured. And so, where we really want to focus on this, we have applications across the board. This is just sort of a collage of things from oceanography to biology. All of these have high data or memory intensive needs on them. Some of the more novel things here are network analyses. These are from the connectome and understanding how human proteins relate. This is an application that will be highlighting at supercomputing, looking at poker as a game of incomplete knowledge. And that turns out to be a highly memory intensive task and very large memory to do the analysis to get reasonable strategies for attacking these sorts of problems. So there are several use cases for data, at least what I think of as data-intensive computing. And there are sure to be more. These were a few that fit well for this talk. And so first of all, for data-intensive computing, I think of this as something where we have a predominant bandwidth component. That could be memory bandwidth or I/O or both, depending on how large the data size actually is, relative to the amount of computation you actually have to do. So first, we have the data parallel analyses. We see a lot of them in this meeting. These are things that fit very well in, say, a Hadoop or MapReduce model, where you have a very embarrassingly parallel, very separable task with reasonably high computational intensity. There are also a bunch of other things, though. There are things where you'd like to do interactive queries on very large data sets. And many of these, if the query is sufficiently complex, you may have to do things across the data. I have examples of that in unpredictable directions, for which you need a fairly tight coupling. There are also various monolithic data sets. For example, in the climate community, there could be individual data sets that will be tens of terabytes as of today. One can imagine sharding those into MapReduce pieces. But inherently, the sort of analysis that people want to do on these today is heavily synchronized. You'd be waiting on the slowest component. So there can still be advantages to having a more tightly coupled analysis. And the other example I have is for really highly indexed data. There are things, again, like they're being done at UW in Quinn's group, where in cosmology you have octrees and other very highly structured data. And in those cases, the inherent indexing in this can give you advantages in the analysis. And so for things like that, we really need a lot of bandwidth to get from whatever the persistent storage is. And so I want to mention this. Persistent storage is something I think is being underestimated anymore. People, especially at meetings like this, figure that you can have a data-intensive resource and you can do your computation. That's all well and good, provided you can store everybody's data. But until we have enough computers for everybody to do this, there will be competition for these. And so one has to think about how you stage data in, how you stage it out, and how you move data between different user jobs. So a few examples I wanted to use to motivate this. One is that we do analyses with the University of Oklahoma every year on prediction of severe storms. And there's what they call a spring campaign that coincides with tornado season, when tornadoes plow across the middle of the United States, to do real-time data assimilation, get predictions for the next few hours. These involved this spring heavy computation on BigBen, which is next T3 at Pittsburgh, some computation at Kraken at the University of Tennessee, Oak Ridge, and also some work at Oklahoma. So I'm going to focus on the PSC piece because this is the one that actually involved fairly heavy data transfer. So I have till what time? I just want till 2:15. Okay. Okay, so I'll keep moving fast. So anyway, this was running a PSC on about 800 cores of BigBen. These are things that run daily at pre-scheduled times. They produce a variety of data products, ensemble forecasts in different modalities. And that gets us to something that was brought up earlier in this session today, which was the importance of knowing the uncertainty of your predictions. The data transfers for this were about 1.5 terabytes a day, or 1.25 terabytes a day. And then they were assembled in Pittsburgh. This is a case now where we have data that's being computed and assimilated from different sources in the field, like radar, and coming across, and then the data are being collected. Another quick example I want to show to motivate just this sort of scale of multiple terabytes per day now is from high-speed transmission electron microscopy. This is an image from Harvard where the instrument actually lives. What we're doing is producing these slices across biological data, mechanics aside, to give you an idea of data size. This is one slice of the image. The little rectangle at the bottom right is the visible human data set that was so popular, 6 years ago, somewhere around there. So each slice of this data set dwarfs the full visible human data set. And we're going to simulate massive numbers of these slices to reconstruct volumes. Now this is at 40 nanometers per pixel. At that scale, we can't yet do the connectivity to look at synapses and actually build the 3D structure of cells. Going down to 4 nanometers per pixel, now we can actually start seeing the synaptic junctions. And so the problem changes to one of segmentation, image reconstruction, building 3D morphology. So what they really want to do over the next 6 months is do 10 terabyte data sets of this and eventually evolve up into the connectome, which is going to be a model of, say, a cubic millimeter human brain. in terms of data movement, what's significant here is just we're looking at data coming from Harvard across a RAID device there into an archive or PSC. And, well, I just want to move on for speed. So the take-home messages here were that the WAN performance was below the line bandwidth. That's what we find all the time. So when people talk about moving data over grid, doing these data-intensive computing challenges, I'll show that a little more in my next example. One actually has to do a lot of experimentation, a lot of tuning to do this. We've done a lot of tuning of the networks themselves. We have a group at PSC who does network performance analysis and tuning, and also working on improved SCPs and so on. The other thing this group really learned was the importance of checksumming, finding just random data loss all through the pipeline. The last detailed example I'll cover is the Pan-STARRS telescope. This was mentioned at least once at this meeting. A little more detail here. The centerpiece of this is a phenomenally good 30K by 30K pixel CCD camera. Again, it produces these very detailed maps. The key thing, though, here is that the telescope lives in Hawaii. There are data analysis centers across the United States, PSC, Harvard, Johns Hopkins, and also across the Atlantic in England. And so we have a lot of data movement to do. We've done 2 experiments so far to demonstrate and understand what is entailed. The first one was actually very small, using PSC as a staging area. The second one, where we did an 8 terabyte data movement, used a combination of wget and other means to transfer data across 2 oceans. And in doing this, learned a lot about the advantages of rsync over wget. What's selling to me, though, is actually this is all very hard. Moving data for the users is a hard thing. We have very skilled people. We have network teams working on this. They're working on it. Let me just back up a minute. But they're evaluating these different methods. They're doing hand tuning, and they're developing the pipeline. This is a hard thing to do. The other thing is we see the network congestion varies very widely over time. This is just over a day. And of course, you expect this. People are busy at different times of day. A couple examples looking at the future. There's a group at Carnegie Mellon that does seismic hazard analysis, looking at doing earthquake simulations, essentially deducing subsurface geology. What they really want to get to is doing very large numbers of these inverse problems to be able to predict what likely hazard scenarios would be, what areas in the Los Angeles basin would be at risk. And so that becomes a very large problem in terms of data. The other thing that's difficult here is, of course, what they do is a simulation, so you produce a bunch of data in time. Now you want to do correlation functions analysis over the time set, so once you're done, you want to do transposes over these. And a side point I'm going to skip in the interest of time, but I could talk about later, is doing statistical analyses of these large 4D data sets. So there are a couple approaches that I think are really important here. What we see across the board for all of these is data movement. People do computation across the grid, maybe across the world. They may have experimental data coming in from all over, and they have to do analysis somewhere. Yesterday it was discussed, I guess in Garth's talk, whether or not you want to have a separate analysis cluster next to your compute cluster, and that's certainly one way of doing it. But we do see that we have people doing things all over, and that's certainly the way things are moving. So 2 approaches I want to talk about very briefly are things being developed at PSC to address these problems. The first is DMOVER, which really allows you to do scheduled data transfers over distributed networks and also to build in workflow characteristics. So there's more here than I have time to go through. The main key, though, is this portable harness. It lets people very easily build in file transfers to their workflows. So a given computational analysis job may be gated on a data movement job that can then be scheduled. And the advantages are twofold. One is that people can build workflows to incorporate data movement into their overall analysis. The second thing is you could schedule the data movement to take advantage of periods of lower network activity. So you don't need to provision your analysis network bandwidth to be the worst case maximum. You have to provision it to be a reasonable, sustained bandwidth. And then you can schedule your data movement accordingly. You can also schedule the data movement according to how much space you may have on your rotating disk on the analysis system. So in the absence of something like this, you typically have an HPC system or some large cluster or cloud to do your analysis. And somehow you get your data in over grid FTP or something else, and you would do that. Oops. With Data Mover, you would have some other nodes you're allocated to doing that specifically, and those could essentially be the servers, they could do the scheduling, and provide this layer of abstraction and portability. This really removes a lot of scalability limits. It removes the network being your bandwidth to getting data in because you can schedule this. You can increase your capacity on demand by increasing those numbers of nodes. And you can really provide a scalable configuration for users. The other thing it lets you do is separate out the diagnostics and some of the performance tuning features out from where they're usually buried in the system facilities to things that are being user visible now. So if a user doesn't get given the file or set of files, they can do some diagnostics and react accordingly without an administrator and perhaps transparently. And so it has a number of other advantages. It lives over existing protocols, grid FTP, over various forms of SSH, and so on. So again, this can live on top of existing protocols. One thing we're focusing on here is to develop these meta services that can live on top of whatever other people use, other sites. Because you won't get people to change their way of working. They do what they're doing for good reasons. But we can provide a layer of abstraction that lets them add new functionality, performance, and usability on top of whatever they're all doing. So the second thing I wanted to mention is /2. This has a similar idea of federating existing systems, but in this case we're looking at federating parallel file systems. And so the parallel file systems may be anything from Lustre down to, say, Hadoop FS. The idea here is to behave like a file system, but give you other data management capabilities. To have some relaxed consistency ideas that lets you really get higher performance and flexibility, and also ease of use for users. The one thing we hear from users working on grids is they really want a single namespace. This is a good move in that direction. And at the same time, it doesn't require people to change their underlying file system. We're not saying they have to use Lustre or GPFS or anything else. The /name came from the scalable, lightweight archival storage hierarchy. I don't know if it still stands for anything or not. That began quite a while ago as a project with the National Archives. And /2 is the next round of this. It's been used in production for a number of years at PSC, literally handling hundreds of millions of files, many petabytes of data, and providing very nice cache hit rates. That, of course, improves performance. And it really lets us improve capacity by just adding essentially white box level services rather than more expensive things. Again, the emphasis on ease of use. So it manages things on behalf of the user, rather than the user having to do the things I've shown you that people are doing successfully to facilitate large data transfers. The idea here is you want to be able to let users do that easily. You want to be able to get maximum performance from the underlying parallel file system, whatever it happens to be, and to be able to get the files across the network. And so this gives very nice cross-site archiving. Certainly the kinds of things you want to do for these distributed data workflows. It can give you geographic replication for data reliability. And okay, those are the things I want to mention from that slide. So for an example task of this, one might have output coming from, this is the XT3 at PSC, and that might go, the query or the instruction from the user might be, you may want to make a backup geographic copy of it somewhere for security, and you may want to copy it also to do some visualization somewhere else, which may be at the same site or may be across some large distance. And so what actually happens there is that under the covers in /2, you get a copy made to an archiver over here, you get a copy made to some archiver at site B, and also a visualization cluster, which can be there or elsewhere. So I've been trying to stay on track. I think the main points here are that we do have a number of cases where the high-performance computing resource, you still want to have some sort of very large balanced resource to do these analyses. It has to have high I/O bandwidth typically high memory bandwidth. I'm concerned about both because for a lot of these, you're going to be larger than the physical memory of the machine, whatever that memory happens to be. So you need the I/O bandwidth also. And then on top of that, you have to give the users the tools they need, whether they're things like DMOVER or like Slash, so they can actually do the science they want to do. Again, see the 4 o'clock talk for the science examples in more detail. And once you've done that, then you can actually get people to be able to do things across, whether it's a teragrid or a broader collaboration that may span several continents. So, be happy to take questions.
Thank you. So if I have my own workflow management application,
Yep.
like Microsoft Trident, so I implement my workflow in that application. What do I use to connect or integrate my workflow manager with DMOVER?
Okay, so Trident I don't know in detail other than conceptually. But for instance, I would imagine there would be things that you can do. So DMOVER will have functionality that one can invoke. And I could imagine that there may be times when you would want to invoke that functionality to schedule data transfers.
Right,
I don't know if Trident has scheduling data transfers in it.
But I think we do. We'll have another layer.
Yeah.
That goes with Trident. We can schedule work and then schedule the nodes among the backend that is available. So my question is, if I want to use somehow connect my application that controls data process from one step to another,
Right.
which I may call some MATLAB routines or XML generator, however what it is. But then behind the iteration of my data computation, I want to use DMOVER just to scheduling and then distribute among the clusters. And
Right, so right now... Oh, okay.
so the question is if I But the question is if I have my own application of workflow management, I was asking how easy it is, or what do I use to connect my workflow application with DMOVER?
Yeah, so in terms of, as I said, I have not used Trident, so I can't really speak to that directly. In terms of the more generic workflows that would be on Linux or grid-type systems, which Trident may be very well, there will be commands for, say, getting a file. There will be commands for gating execution of some tasks, maybe analysis or something else, on the arrival of that file. Now, I don't think it's in DMOVER now, but there's a lot of functionality by having this as a separate layer for being able to do those scheduling. I'm sure this part is in DMOVER for being able to do that sort of scheduling system-wide. So if you have a number of users running independent workflows on a given resource, you don't want them all to initiate transferring 10 terabytes in at once.
Oh, okay.
So that sort of scheduling are things that you can do also to maximize your overall throughput given the network capacity that you happen to have.
Yeah.
I think what you need to do in Trident is you need to build a wrapper for DMOVER.
Yeah, probably. There is an interface in between that we probably need to do.
Yeah.
Right.
We can take that off.
Yeah, and I'm sure those things can be done.
Thank you.
In the same way with
Yeah,
right. So DMOVER would sit on top of grid FTP, or that's one layer it could sit on top of. And so the same way you're calling grid FTP now, you could call DMOVER instead and get a little bit more flexibility. And similarly, the federation file system through /2, that could also be transparent to a Trident layer or anything else.
Yeah.
Right.
Yeah, thank you. Any more questions? Thanks again.
Okay, thank you.